Well, hey there, everybody, and welcome to the fifth and final episode of Takeo After Dark, the summer sessions. This is going to be exciting. What a finale for this beautiful summer that we've had, or this hot summer that we've had, or depending on where you are, this summer of floods, this summer of wildfires, this summer of oppressive heat, or whatever. Okay, we've been through thick and thin together, and this is our final edition of this summer session. I'm John Barba from Takeo Comfort Solutions, along with my able companion, Mr. Dave Holdorf. How you doing, Dave?
I am wonderful today. How about yourself, man? How was
I
the drive
am
home?
It was frantic. It was frantic. It was a 2.5 hour drive home just to make sure I got back from our factory in Cranston to my home office here in Exeter, New Hampshire, to be sure I'd be ready to be right here with you, and ready to rock. So it was a frantic 2.5 hour dash, but we made it. Also joining us, and we can't see their handsome faces, are Tim Ward and John Messenbrink from Mechanical Hub. So come on in when you can, gentlemen. Say hi to everybody else.
Woohoo!
The big train, the big train. All right. Yeah, tonight we're gonna have some fun tonight in our final episode of the session, and Bruce Campbell approves. This is a Bruce Campbell approved episode. Again, as we've said many times, Bruce Campbell is the most interesting living American as far as I'm concerned. And Dave Holdorf is a close second, but Bruce Campbell is the most interesting living American. And tonight's episode 5, flow, head, and circulator sizing fundamentals. We're going to get right down to it. Why it's important. How do you figure this stuff out? What happens if you oversize the circulator? What happens if you undersize the circulator? And how do variable speed circulators fit in? What do they really do? And do I need to know all this stuff if I'm using a variable speed circulator? I'll give you a hint right now. The short answer is yes, absolutely, you do, but we'll get into some of the details of that this evening. So real quick before we get started, just one last recap. If this is your first time, a quick recap of what the control panel is all about. You have your audio section, handouts, which I'm sorry, again, we don't have any this evening. And then most importantly, the question/chat section down in the bottom. You all should know what to do at this point. If you could type in a hi, hello, how are you? So I know that you know how to do that, and that I know that you can hear me, which is also very important. So type that in and let us know what you think. This is where you're going to be asking your questions, of course, and all questions are fair game. All questions are obviously encouraged. We want to know what you think. We want to know that you're with us, and we want to keep this kind of interactive. So please make sure you ask plenty of questions. Plenty of questions. And if you're on a tablet or a phone, it's going to look a little bit different. Okay, Dave's going to have that little sulky look on his face as he has right there. So you can toggle back and forth between webcams and the presentation there. You've got, again, your audio settings and that question mark down in the corner. That's the important one. That is where you're going to actually ask your questions. So there we go. Where is Dave? In a closet? No, Dave's in a hotel room right now. He's actually in a hotel.
Yeah, I'm not in my typical office or basement, as in we show in the closet picture. Yes, I mean of the sulking picture from before. You know, that was in the old basement. I was probably trying to stay warm at that point. So, but no, I am in Warwick, Rhode Island right now. So John left the factory earlier. He gets home in about 2.5 hours. I get home in 4. So I couldn't make it home. Otherwise, I wouldn't be able to join you tonight. So I'm staying in Rhode Island tonight. We'll head home in the morning.
There you go. There you go. And you're right, Richard. It's not Warwick. It's Warwick, Rhode Island. Hey, John and Tim, just share with the group what's going on with Mechanical Hub this week. So they're up to date and know where to find you.
JP, you want to take that? I'm just staring at Eric's face here and wondering where Eric is right now.
It is disturbing, isn't it?
Well, I will say, last week we had a road trip, the first work trip in about 15 months. We went up to what was it, Tim? Southwest of Minnesota, or Minneapolis, where kind of your old stomping ground, John.
Oh yeah, Shakopee was next town over. Yeah.
Yeah. So we visited a company called Churney, and they make test ball plugs. And it was really interesting. So we got the tour and we took some videos and all that good stuff. So that'll be probably processed and on the site in a couple of weeks. So we're excited about getting back on the road and doing normal, quote unquote, stuff. So
Exactly.
Oh, excellent. That's good. I hope we can keep doing it too. I hope we can keep doing it. Now, obviously, we don't have Eric with us again. Well, shockingly, we don't have Eric with us again tonight, do we? Eric Ani's the third member of Mechanical Hub, and he's kind of basically the curly of the group. I mean, Mo and Larry are in charge. Eric's the curly. I guess he is. We've invited Eric to every single Takeo Mechanical Hub Takeo After Dark that we have done, and we have seen Eric exactly 0 times over that time, and it's getting hard not to take it personally. But because we love Eric, we want to find out where Eric is. So this is sort of Where's Waldo tonight, but with Eric. So we're going to play Where's Eric, and what you guys are going to do once you have a good guess of where Eric is, you're going to type it into the question section, and if you get it right, you'll be entered in a drawing for a prize, which will be a Takeo After Dark T-shirt, kind of like the one I'm wearing now. Okay, so where in the world is Eric? Where is Eric? Let's see. Where is Mr. Ani? Whoa, now where is that? Where is that? And what is the significance of that place? All right. So where is Eric? Where in the world is Eric, and why is Eric's location significant? So I'm going to leave that up for a couple seconds, and then your job is to come up with an answer. And if you get it right, you'll get entered into the contest to win a T-shirt. All righty. Looks like we got some answers coming in. Let's see. Well, no, we don't have any answers coming in. How about that, huh? Nobody seems to know where Eric is.
I have a guess.
You have a guess. Well, you can type it in, but you can't say it out loud. Come on, man. That's not how this works. All righty. So think about it. Type it in when you got it, and let's get this show on the road. And here are tonight's cast of characters. While this duo could also pass for John and Tim, they also pass for John and Dave. Now, Dave, one might get the impression here that Dave is my caddy. Okay, no, he's not. He's about ready to hit me over the head with a 9-iron in this picture, because that's kind of the way it works. We're both golfers, so we're both golfers, and we're both trainers, and we both love the Flintstones, because what's not to love about the Flintstones? All right, with Barney and Betty and Fred and Wilma, that's us tonight. So Flintstones, meet the Flintstones. We're right here, and the Flintstones will be the subject of tonight's Takeo trivia question, which we'll be getting to in just a little bit. Now, all the preliminaries are out of the way. Let's get started on our topic tonight: flow, head, and the finer points of circulator selection. The finer points of circulator selection, yabba dabba do. Okay, yabba dabba do. Flow and head. It's everything in circulator selection. It's all flow and head. Circulators are designed to do one thing, right? Circulators are designed to do one thing. They're designed to facilitate the journey of BTUs from the boiler to the heat emitters, all right, and to try to do it as effectively, as economically, and as efficiently as possible, all right, and to do it at the right rate, That's what circulators really do. If you were to put a name on it, we call them pumps, but yeah, that's okay, shorthand, we can live with that. But in fact, what they really are circulators, or more precisely, pressure differential machines. Whatever comes in goes out at a higher pressure. They create pressure differential. At that point, Mother Nature takes over. High pressure always goes to low pressure. And when high pressure goes to low pressure, well, flow will ensue, okay? So the trick here is to get a circulator that creates enough of a pressure differential to give us enough flow when we need it, okay? When we need it is the key word. So you cannot separate flow and head. Flow we determine, of course, in gallons per minute, GPM, gallons per minute. How many gallons per minute do we need to deliver to a heating zone or a heating system in order to deliver the BTUs required? Okay, that's kind of a great way of thinking about flow rates. And here's the thing about how flow and head go hand in hand. When flow goes up in a system, the head loss or the pressure loss or the friction loss, the resistance the flow encounters going through the pipe, will go up exponentially. As flow increases, head loss or pressure loss will go up exponentially. It's a function of the square of the flow increase, as you'll see. So if I have 2 gallons a minute and my pressure loss is 4 feet of head, all right, if I all of a sudden go to 4 gallons a minute, I don't go to 8 feet ahead. In fact, I'll go up to about 16 feet ahead, okay? I'll go up to about 16 feet ahead. That's kind of how that works. Flow goes up, head loss or pressure loss goes up exponentially. Again, we'll show you the math behind that, okay? But first I want to show you the math on how to calculate flow. How do you get your flow rate? In order to get your flow rate, you need to know 2 things. You need to know the BTU load of whatever it is you're sizing the circulator for. It could be a zone, a single zone. It could be, if it's a zone valve job, it could be for the whole house, okay? You need to have a good idea of the flow rate. The best way to figure that out is, of course, to do a heat loss analysis. Hey, you know, you're replacing if you're doing a job from the ground up, or you're doing a big old boiler replacement and you're replacing the circulators, I recommend doing that. That's really the smartest thing you can do. If you got a dead circulator and you're replacing a dead circulator with a new one, you're not going to do a heat loss analysis for that zone, okay? It's not going to happen. What you will do is you'll go back to two sessions ago, or 3 sessions ago, I believe, when Dave showed you how to select a replacement circulator without doing the math. That means you know the pump curves of the circulator you're taking out. That aside, now we're going to do it with math. GPM, which is your gallons per minute flow rate, is equal to the BTU load that you have to deliver under design conditions divided by the designed for delta T. What delta T are we designing this system for? Typically, residential hydronics are designed to a delta T of 20. All right, 20, a 180 out, 160 back, average water temperature of 170. Low temperature systems with a mod con, it could be 140 out, 120 back, average water temperature of 130. That's a 20-degree delta T. There's nothing sacred about 20. It's just what we happen to design systems to. And if a system's designed to 20, then it's designed to 20. There are some, snow melt systems are often designed to 30. Residential radiant systems are often designed to 10. It can move, but most cases we're going to be designing to a delta T of 20 because that's what the system was designed for originally. And then we BTUH divided by the product of delta T times 500. Delta T times 500. Now, what is 500? 500 is kind of what's the word? It's kind of a rule of thumb for 100% water. We're talking about the weight of 1 gallon of water. 1 gallon of water will weigh 8.33 pounds. So we multiply 8.33 pounds times 60, which is the number of minutes in an hour, 8.33 times 60, times the specific gravity of the fluid. That specific gravity of 100% water happens to be 1. So it's 8.33 times 60 times 1 times the specific heat of the fluid. And 100% water has a specific heat of 1 because, after all, it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit, 1 hour. It's a whole lot of ones, right? 8.33 times 60 times 1 is 499.8. We'll call her 500. Okay, that's where the 500 comes from. You start throwing glycol into this mix, that number's going to go down. Okay, the more glycol you put in, the more that number goes down. You got maybe a 30% glycol solution, that number might go down to about 470 or thereabouts, depending upon the product. If you go 50-50, like for a snow melt system, that number might go as low as 430, 435. All right. The more glycol you put in, the lower the 500 gets. And the lower that 500 gets, the higher the GPM you'll need to deliver the BTUs required. Okay, that's kind of how that works. So GPM equals BTUH divided by delta T times 500. So the 2 numbers you got to know the BTUH as best you can, and then you got to know, have a good idea of what the system was designed for. And for most cases, 20 is a really good guess for most cases. So let's figure this out. Let's say I've got a zone that's 30,000 BTUs. That's a big zone, okay? Understand this, that's a big freaking zone. 30,000 BTUs is a huge, huge zone. That's a lot of baseboard. That's 60 feet of baseboard, right? At 500 BTUs per foot, if you're thinking about that. 30,000 BTUs is a lot of zone, okay? So I'm going to size this circulator for 30,000 BTUs, and my delta T, of course, is 20. So 30,000 divided by 20 times 500. Now, 20 times 500 is 10,000. And you can divide anything by 10,000, which is one of the reasons why 20 is the delta T we designed to. It makes the math easy. So in this example,
that's not the only reason why we use 20.
No, but it's a big
It's a nice reason.
It's a nice reason. It's a nice reason.
It just so happens to work out that way. And, you know, and actually, and Mark was saying before about the 20, that's also what a lot of boilers are tested to get their AFUE.
Exactly. That's right. That is right. Okay. So now you can do, now the math's easy. 30,000 divided by 10,000. Well, Glorioski, Captain BTU, what is that? That's a gallons per minute requirement of 3. So my circulator is going to have to deliver 3 gallons a minute under design conditions in order to deliver 30,000 BTUs. So I'm going to have to move water at a rate of 3 gallons per minute in order to deliver 30,000 BTUs. And when do I need that 30,000 BTUs? On the quote unquote coldest day of the year, whatever my design temperature is. Now understand this, how often are we at or even near our design temperature? Dave, any guesses?
About 2%.
Yeah,
2%. You blink, you miss it.
Exactly. It's about 2 to 2.5% of your average heating season. Now we're sizing everything for that little itty bitty point in time, that blink if you miss it point in time, because that's the one time we always said, well, nobody wants the phone call middle of the night, Christmas Eve. I don't know if middle of the night, Christmas Eve is any better than middle of the night, you know, February 2nd, but hey, that's the way it goes. We don't want the phone call, right? We don't want the phone call. We want to be able to deliver enough BTUs when it's generally as cold as it ever gets. All right. And that's, again, 2.5% of the time. We will spend a good 50% of your average heating season, at 1/3 load or less. 50% of your heating season is spent at 1/3 load or less. Now think about that. What's 1/3 of 30,000? Well, 10,000, right? 1/3 of that load is 10,000 BTUs. 50% of your heating season is spent with a load of 10,000 BTUs or less on that one zone. Just keep that in mind. You know, 50% of the heating season, that zone actually requires 1 gallon a minute or less in order to deliver the BTUs required. So understand what we're doing here, okay? All righty, so there's your flow. Flow doesn't get any more complicated than that, really. It's pretty straightforward. Now, head loss, we got to understand a few things. What is head loss? Well, head loss really is a fancy term for friction loss. Friction loss is, you know, most normal people, when they think about friction loss, they think about it in PSI, right? I started with this PSI, I run through some pipe, the water rubs up against the pipe, and that's friction. Okay, it's going to lose a little bit of pressure as it goes through here, right? That makes sense. That's friction loss. For some reason, and friction loss you can express in PSI. For some reason, in our world, we choose to call it head loss. All right, we choose to call it head loss. Why? I don't know, but we do, and that's just the reality of the situation. Now, the piping in the system creates that friction. The water rubbing up against the pipe causes the friction, it causes the friction loss that the circulator has to overcome. So my circulator has to provide enough of a pressure differential, like we talked about earlier, through that piping system in order to deliver that 3 gallons per minute. Maybe the best way to think about it, who remembers playing with this guy back when you were a kid? I love these things, man. I was a Hot Wheels freakazoid when I was a kid. I loved them, and I would spend all day on a rainy Saturday racing my Hot Wheels head to head on those little drag strips that they made with the loop-de-loops and stuff, going down, you know, connecting it to my mother's dining room table and getting yelled at for doing it and scratching the table. But hey, this was important stuff. And they'd run through, and I'd just do a runoff to see which was my fastest Hot Wheel. Well, then 1969 came about, 1970, and this thing joined the race, the supercharger. Now, the supercharger was this little hut there, this little garage that had these big old rubber wheels in it, you know, and they had batteries, and the rubber wheels would spin, okay? And the car, you just put the car on the track, the little orange track, and you'd roll it into that supercharger, and then poof, the thing would just shoot out like crazy, and it would zip around. So now you didn't have to go, you know, put scratches on your mother's dining room table. You could put it flat on the ground and have it go round and round in circles like that, which was wicked cool, man. That was the supercharger. That's what it did. Now, think about it. If you want to think about it like this, the Hot Wheels, the cars themselves are like the water, okay, in the system. The orange track is the pipe, all right? The orange track is the pipe, and the supercharger is the circulator, okay? Because after it goes out of that supercharger, the car goes rattling around on the track, okay? And it's slowing down as it goes around the track till it comes back into the other end of the supercharger, and bam, it shoots right back out again, okay? That's kind of how that's how a circulator works. That's how a hydronic heating loop works, and that's how a supercharger works. Anybody play with these when you were a kid? I loved them, man. I could just spend hours and hours and hours with
What do you
Hot
mean?
Wheels.
What do you mean as a kid?
Did you still play with them?
Of course.
All right. All right. Excellent. 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 So yeah. Douglas played with Hot Wheels. Jerry, you still have yours? Good man. Good man. All right. I loved them. My favorite was it was like a gray kind of station, or no, a purple station wagon. I think it was called the Nomad. I love that thing. I love that thing. And then there was the one that was like a flatbed and it had the two surfboards that you put in the back. And everybody who had that thing lost the surfboards inside of 2 weeks, right? I lost mine. I think I might have lost mine the day I brought it home, but that's just the way it is. I love me some Hot Wheels, man. My nephew got them, and when I grew up, and I don't know where they are now, which upsets me. There you go. All righty. Cool. Oh, Sarah, my friend sent me a Hot Wheels car in the mail yesterday. How cool is that? All right, Travis, I got kids, so of course I still play with Hot Wheels. Excellent. You didn't play in the dirt? Oh, God, yes, I did play in the dirt, too. The mongoose and the snake. I had those guys. I did have the mongoose and the snake, Jimmy. All right, excellent. I love it. We've got Hot Wheels Freakazoids. This is terrific. All right, let's figure head loss. Now, there's an easy way to figure head loss, but I want to show you the right way because the right way is going to be instructive. Figuring head loss. This chart comes from the Copper Development Association's Copper Tube Handbook, and it's in one of the appendixes, and it's really the most useful thing in there. And what this Table 6 does, Table 6 gives us the pressure loss of water due to friction. All right, you can see that right up here. Pressure drop in water due to friction in types K, L, and M copper tubing. Now, what's important to note here is, okay, it gives it to us in PSI per foot of tube. PSI per foot of tube. PSI per foot of tube. We're going to have to convert PSI to feet of head, and I'll show you how to do that in a second. So, let's say we're going to be using 3/4 inch M copper for 3 gallons a minute. As our pipe sizing guidelines would tell us that 3 GPM, and we're going to use 3/4 M copper right there. So we're going to use this column right here. All righty. So 3 gallons per minute, 3/4 inch M copper. If we follow 3 gallons a minute over this away, 3/4 inch M down this away, and we will find that the pressure loss of water due to friction in 3/4 inch M copper at 3 gallons a minute is 0.009 PSI per foot of pipe. The next thing we want to do is multiply 0.009 PSI per foot of pipe by the amount of pipe in the run. And how much pipe is that? Well, you start at the gazouta side of the circulator, you go all the way through the run, through everything else, back to the gazinda side of the circulator. You figure all that run in linear feet. Well, do you have to get in there with a tape measure and measure every inch? No, that's unrealistic. The best you can do here is if it's a retrofit or something like that, or you're replacing a boiler and you don't know how long those runs are, you do an intelligent, educated estimation, which means you've run pipe through houses under construction before. Your best bet here is to say, okay, here's the circulator. I'm going up 10 feet. I'm going over 10 feet. That's 20 feet. All right, I'm going down 40 feet. That's 20, 40, 60 feet. I'm going over 20 feet. That's 80 feet. I'm coming back 40. That's 120 feet. I'm coming over 10. Okay, that's 150 feet. I'm coming down 15. That's 165 feet, more or less. I mean, as Dave has said in many of our presentations before, if your estimate number ends in anything other than a 0 or a 5, you're overthinking it, okay? Estimate as best you can. Don't guess, estimate, because you're using your experience to kind of say, all right, if I were a pipe, how would I get through this house, all right? And you include the element, everything, right? Once you have that estimate, you have to allow for valves and fittings and things that are in the way. All right, valves, fittings, things that are in the way. The best way to do that is to simply multiply by 1.5. All right, you're adding 50% to the length to allow for valves and fittings and stuff that's in the way. So whatever number you get, you multiply it by 1.5, and that equals your total developed or your total equivalent length. So measure, estimate the length, multiply it by 1.5. That's your total developed length. If we straightened out all those fittings and had just a pipe in one big old circle, that's how big the circle would be, or how long the circle would be. Again, for an example, a 3/4 inch copper elbow has the same pressure drop as 2.5 feet of straight copper pipe. Okay, a 45 has the same pressure drop as 1 foot of pipe, et cetera, et cetera. We're trying to estimate that without actually counting the fittings, okay? So in this case, we do our math, we multiply by 1.5, and we come up with a total developed length in this example of 285 feet. That's a long zone, man. Okay, that's about 100 and it's almost 200. That's about 180 feet, 190 feet, about 190 feet, I'd say. 190 foot long times 1.5. Okay, it'll give us about 285 feet total developed length, fittings taken into account.
That's also counting the 60 feet of baseboard that you had there too, don't forget.
Exactly, that includes the 60 feet of baseboard, absolutely. So you multiply that out and you have a pressure loss in terms of PSI of 2.57. Now we have to convert that to feet of head. Now, if you went to plumbing school, if you got a plumbing license, you might have learned this like day 1 or day 2 of plumbing school, is that a column of water 2.31 feet high will have a gauge pressure at the bottom of 1 PSI. Doesn't matter how big around it is, it just matters how high it is. So 28 inches or 2.31 feet high. The gauge at the bottom would read 1 PSI. That's the head pressure. Okay, that's just that has to do with the height of the water. So we have used that relationship to say that 1 PSI of pressure drop is equal to 2.31 feet of head or feet of head loss. So to determine our head loss, we're going to multiply our PSI pressure loss of water due to friction by 2.31. That's 2.31 PSI or 2.31 feet of head per PSI. So let's math that part out. 2.57 PSI times 2.31 feet of head per PSI per foot of pipe, okay, is going to equal 5.9 feet of head. So my total pressure loss in that zone or in that run of pipe at 3 gallons a minute, that's the important part, at 3 gallons a minute, is 5.9 feet of head. So when I'm looking to size a circulator, what am I looking for? I'm looking for a circulator that can do 3 GPM at 6 feet of head. That's what I'm looking for. When I want to size a pump, that's what I'm looking for. All right. Any questions out there, Dave?
Nothing, man. Nothing. We just had lots of people answering the proper answer on Where's Eric.
Oh, good.
We're rocking and rolling. So nothing so far.
Terrific, terrific. It makes me want to hold their hand. Oh, hint, hint. You know, but money can't buy me love. That's the truth, right?
That's right. That's right.
Roy.
It can buy some other things too. Yes.
It can buy some other things, but it can't buy me love.
We need that car. You know that Fred drives. You know.
There you go. That's right. That's right. Okay, now let's talk about system curves real quick before we get into figuring, how to figure out what these things are and what really happens. Because we just went through a lot of rigmarole to find, let's say, 3 gallons a minute at 1, 2, 3, 4, 5, 6 feet ahead. Okay, we did a lot of math there. But depending upon what circulator I put on this job, I may never see 3 at 6. 3 gallons a minute at 6 foot ahead might as well be a figment of my imagination once I throw a circulator on here. All right, this is why circulators, understanding this part and understanding how circulators impact your system is going to make a big honking difference in the performance of the system. So let's talk about system curves for a minute. Because remember, as we said, as flow goes up, head goes up exponentially. So as flow goes up, head will go up exponentially. It's a function of the square of the increase. Okay. And what we do, we know a system curve is a theoretical hydraulic fingerprint of the system. We know, because we did the math, that at 3 gallons a minute, there's 6 feet of pressure loss or 6 feet of head loss in that piping system. I also know another point on that on that plot. Remember when you were doing charts and graphs in like 5th and 6th grade math, and you thought, some freaking waste of time, man. I'm never going to use this crap ever in my life. Hey, guys, today's the day. Okay, today's the day. You are going to use charts and graphs and how to plot things on a graph and figure out where they go and why they're important. That's what we're going to do right now. We know 3 gallons a minute at 6 feet ahead, but we also know one other point on this chart, and that's 0 gallons a minute. They're 0 feet ahead. So all system curves start at 0, 0, and then they go up and to the right, depending upon the relationship between flow and head. And that's a fixed relationship, all right? That's a fixed relationship. And there's a math formula, which you're gonna love, that's gonna help you plot out a system curve. Are you ready for this? Dave, I know how much you love math. Are you ready for this?
Let's see it. Let's see it. Let's do.
I want to show of hands out there. How many of you guys are just be digging math, man? How many of you guys are digging the math? And I don't need to hear from you, McGrath. I know you love math, man. I know you love math. How many really cannot wait to jump all over this system? Yeah, closed systems only start at 0, 0. That's what we're talking about, right? That's what we're talking about. All right, Kevin's just giddy with excitement. All right. Oh, Stefan loves the math. Sarah loves the math. Okay, cool, cool, cool. Let's do the math, man. Let us do the math, okay? Because math will never, ever lie to you, all right? And here's the formula. Head 1 divided by head 2 equals flow 1 divided by flow 2 squared. What the heck does that mean? Well, we know 2 items here. We know flow 1 and we know head 1. Flow 1 is 3 gallons a minute. Head 1 is 6 feet ahead. Flow 2 can be whatever we want. All right, we can put in different numbers for flow 2, and then we'll follow this math formula to figure out what head 2 is. All right, so let's say I know my flow 1 is 3 gallons a minute, and I know head 1 is 6 feet ahead. But now I want to find out, well, what's the head loss at 6 gallons a minute? That would be flow 2. I'm going to put 6 gallons a minute in at flow 2, all right, just to see what it is. So head 1 divided by head 2. I don't know what head 2 is. So in algebra, head 2 is x. So in this case, 6 divided by x equals flow 1 divided by flow 2. So that's 3 divided by 6 squared. All right, now it's kind of basic, simple math. Let's figure this out, all right? So 6 divided by x equals 3 divided by 6. 3 divided by 6 is 0.5, right? Because 6 goes into 3.5 times, all right? So 3 divided by 6 is 0.5. 0.5 squared, okay, is what we're looking for. So 6 divided by x equals 0.5 squared. All right, this is getting fun. I told you it's going to be fun. Let's simplify even further. 6 divided by x equals 0.25. So 0.5 times 0.5 is 0.25, right? 0.25. Now, in algebra, we want to solve for x. So we got to get x off of one side and put it on the other so we can solve for x. First thing I want to do, get the x off of the dividing side. I want to put it on a multiplying side. So 6 divided by x. If I multiply both sides by x, because with algebra, whatever you do to one side, you have to do to the other, right? 6 divided by x times x is going to equal 0.25 times x. So 6 divided by x is 6, right? 6 divided by x times x is 6. 0.25 times x is 0.25x. Now we saw how to solve for x. I simply multiply both sides times 0.25. Now I'm isolating x. So I'm solving for x. X divided by 0.25, 0.25x is x. All right. 6 divided by 0.25 is 24. So you see, I doubled the flow. 3 gallons a minute went up to 6 gallons a minute, and now with the head went up to 24 feet. Okay, it just didn't double the head; it quadrupled the head, right? So 6 gallons a minute, my head loss is 24 feet ahead. Now, that's a lot of math. That's a lot of math. Don't expect you to know that. If you're going to plot out a system curve, there's a way, way, way easier way. And I always get in trouble with this because I bring in, one of our competitors' marketing materials, but to me, it's one of the most useful things ever introduced to the industry, and that's the Bell and Gossett system sizer wheel. And actually, I have a copy of the original hand-drawn Bell and Gossett system sizer wheel, hand-drawn by Gil Carlson, the godfather of North American hydronics, about 5.5 feet, no, but that's 7 feet that way, okay, sitting on my wall. If you go to scale 5 on the B&G system sizer wheel on the back of the thing, you'll be able to plot out a system curve, and you'll be able to do it in about three seconds, okay? The first thing you do, okay, see this upper portion right here says feet ahead, right? In this white window, here is GPM. So what you want to do is line up your known GPM, which is 3, with your known feet ahead, which is 6. Now all you do is you read that way and you read that way to find the head at different flow rates. So let's say I want to go back down this way. At 2 gallons a minute, if my flow rate through that piping system was 2 gallons a minute, the head loss through that piping system would be less than 3 feet ahead, right? It would be what, 2.567, about 2.7 feet ahead. If I go down to 1 gallon a minute, right here, 1 gallon a minute, I'm at 0.7 feet ahead. All right, do you see how that changes? As flow goes down, head goes down dramatically. Now as flow goes up, head goes up dramatically. So from 3 gallons a minute to 4 gallons a minute, I go from 6 feet ahead to 11 feet ahead. I go up to 5 gallons a minute, 18 feet ahead, 6 gallons a minute, I'm back at that 24. Okay, and you see where it goes. So now I have all those points on my plot. Okay, these are all my points going up to 8 gallons a minute and I'm up to 42 feet ahead. Okay, so I've got all of those points on my plot. Now I can go to my chart and plot them out and connect the dots, and I'll have my system curve. And why are we doing this, man? Why are we bothering? Well, let's put the points on the plot first. Okay, so now we plot those out. Okay, those are all my data points for my system curve. And then, whoops, okay, excuse me. Those are my data points for my system curve. Now, if I connect them, all right, excuse the artwork, all right, there's my system curve. The reason the system curve is important is because every single system on the planet will work this way. The system will work where the system curve intersects the pump curve that you've chosen. The system will work where the system curve intersects the pump curve that you've chosen. I've talked to people who were, again, self-proclaimed experts, and I had one guy tell me, the system's gonna do what the system's gonna do. Oh, hell no. Energy in equals energy out. That's the law. All right, that's the law. The system's gonna do what the circulator tells it to do. In this case, a fixed speed circulator says you will do what I say. You will operate where I say you work. I don't care where you want to work. You're going to work where I say you work. That's how systems actually operate. Here's an example. Okay, let's plot out that system curve here with the TACO 0015 standard efficiency circulator. It's a standard efficiency 3-speed circulator. Now, quick poll of you folks, where are 3-speed circulators set? What speed are 3-speed circulators almost always set? And I'll give you a hint. Low and medium don't count. Okay, they're almost always set to high, right? Because if a little is good, a lot is better. And if a lot is better, everything the thing has must be the best, right? Or else why would they give us that high speed? We want to be sure, man. We want to be sure. So let's take a look at this. Let's just connect these dots. And again, excuse the shakiness of the mouse here. All right. If I set this thing to high speed, the circulator is going to work right here, right there. All right, at about what looks to be about 4.75 gallons per minute. When how many gallons per minute did I need here? I only needed 3, right? This is all I needed. This is what I needed, but this is what I'm getting. 4.75 gallons per minute at, looks to be about 14.5 feet ahead. In a zone pump application, the head's not a big deal. That's not going to cause you any problems, but the flow just might. I got about 40% more flow than I really need. And here's the thing. Remember we said you only need 3 gallons a minute when? under design conditions, that 2% of the heating season. But I'm giving it 4.75 gallons a minute every day of the heating season. It's always going to get that. What's going to be the result? Let me show you. Okay, math don't lie. Remember, GPM equals BTUH divided by delta T times 500. Well, that's an algebraic equation. We can isolate for delta T. Delta T equals BTUH divided by the GPM I'm using to deliver that BTUH divided by 500. All right, in this case, that's 30,000 BTUs under design condition, all right, divided by 4.75, that's the flow rate I'm giving it, divided by 500, the best delta T, ladies and gentlemen, the best delta T we're going to see in that system is 12.5. We designed it to 20, but we're giving it 12.5 for that 2% of the heating season. That's the best it's ever going to get. That's the best it's ever going to get. If it warms up some, and we're at about 50% load, right? It's about 50% load. That's 15,000 BTUs. That's 15,000 BTUs. And I'm still giving it 4.75 GPM. What's the delta T going to be then? Okay, what's the delta T going to be at 15,000 BTUs? I'll tell you right now, it's easy. Just divide 12.5 by 2, okay, because it's at 50% load. So 6.25. 6.25. So the water's going to go out at 180, come back at 173.5. How is this a good thing? Okay, how is this a good thing? And we spend 50% of the heating season at 1/3 load or less. 50% of the heating season at 1/3 load or less. That's 10,000 BTUs or less. We're going to spend half of the heating season, more than half of the heating season, with delta T's in single freaking digits. What is going to happen at that boiler? Tell me, what do you think the net result is going to be with the boiler? All right, what do you guys think? Yep, you got it. You got it. Short cycling is never, ever good. You're going to be short cycling, right? You're going to be short cycling like crazy. Never, you got a system that's never even going to be close to as efficient as it could or should be. You're telling your customer, oh yeah, we install the very best and most efficient systems. Also, blah, 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 blah. Okay, and you're putting in a very, very efficient boiler. This happens with ModCon boilers too, man. You're putting in the most efficient modulating condensing boiler there is. You're piping this thing up beautifully, and then you're hamstringing yourself. You're intentionally giving that customer about 60 to maybe 65% of what they're paying for. That's the damage here. That's the damage. Okay, and that's just the way it is. That's just the way it is. All right, real quick, because we might be running a little long here. Because once I get going, I don't shut up, right? Let's talk Flintstones. Let's talk trivia. Tonight's trivia question is, in the TV show, Fred and Barney belonged to a lodge. They were lodge brothers. The question is, what is the name of Fred and Barney's lodge on the Flintstones? What was the name of their lodge? All right. What do we have for a prize tonight, Dave? Do you know?
Do I have any prizes?
Yeah.
I'm not at home, so I have no idea.
Oh, you have no idea. You don't know what you got.
No, I don't know what I got in the basement. What? So you tell me what I'm giving away.
We'll give away something pretty cool. We're gonna give away something pretty cool tonight. I think it's gonna be something that's gonna vary its speed. I don't know what yet. Something that will vary its speed. That's what's gonna go out tonight. All righty. What is the name of Fred and Barney's lodge? What is the name of Fred and Barney's lodge? All right. Yabba dabba doo. All right. Let us continue. What about a zone system? If I had a zone valve system in there, zone valve system, okay? With a zone valve system, you got a whole bunch of system curves, right? You got a system curve for every possible combination of zones that could be running at a given point in time. You know, for an example, a 3-zone zone valve system has 7 different system curves. All right, let's count them out. You've got zone 1 by itself, zone 2 by itself, zone 3 by itself, zone 1 and 2, zones 1 and 3, zones 2 and 3, and zones 1, 2, and 3. That's 7 different system curves. So you have 7 different system curves, and you have 7 different points of intersection on the pump curve, right? So 7 different system curves, 7 different points of operation. So let's take a look at this guy. We're going to do this ModCon boiler thing, and we're going to be talking obviously about this circulator here. And that circulator requires 7 gallons a minute at 5 feet of head loss. 7 gallons a minute at 5 feet ahead. All right, that's what I want. That's what I need. And I'm putting a 007 on it, a standard efficiency 007. Okay, so right here, here's my 7 gallons a minute at 5 feet ahead. That's what I need. But with the 007, the best I'm going to get is out here. Looks to be about 9.5 gallons a minute. It looks to be, oh, I don't know, almost 7, maybe 8 feet ahead. That's with all zones calling, right? Forget the 8, 7s, whatever. That's just these are my system curves. So we add the circulator, okay? Now, as zones close, right, the system curves change and we back up the pump curve. So flow goes down. It's a fixed speed circulator, right? But as zones close, flow goes down. It has to, right? Because I got fewer holes for the water to go through. But because I'm working on a fixed curve, as flow goes down, in this example, the head pressure differential has to go up just a little bit, right? It has to go up just a little bit, up just a little bit. Flat curve pumps like the 007 are perfect for zone valve applications. They're perfect for zone valve applications. Why? Because big changes in flow result in very small changes in delta P. I'm sorry, it says delta T, you say delta P. Big changes in flow result in very small changes in pressure differential created by the circulator. Now that's important. That's important. It keeps the flow rates a little closer to where they should be. Ideally, they're not right on, but it keeps them closer. But it also helps keep the system quiet. Let's compare it to a steep curve pump. Let's say this is a Takeo 008 or the 0015 standard efficiency at high speed. Your Grundfos 1558 at high speed, the B&G NRF 22 at high speed. They're all really close to the same circulators. Again, system curve's going to intersect here about 9.5 gallons a minute, pretty doggone close to what I had before. And the head's going to be reasonably close to what I had before too. But again, now as these zone valves close, my system curves back up the pump curve, but they're intersecting at higher and higher and higher pressure differentials. So now as flow goes down, the head pressure differential created by the circulator goes up a lot, And the circulator is creating very high pressure differentials. What does that mean? Well, big difference in flow, or even in some cases, small differences in flow equal a big difference in delta P. What happens when a zone valve closes against 15, 16, 17 feet ahead? What do you think is going to happen when a zone valve closes against 15, 16, or 17 feet ahead? What do you guys think is going to happen out there? Any guesses? Any guesses? Yeah. Is it going to be making some noise? There we go. Bang, bang, water hammer, thump, thump, thump. Absolutely. That's what's going to happen. You're going to get banging and you're going to get noise, which we don't want, Now, how do we deal with it? Well, we have some choices. Simplest thing to do is why put on a steep curve pump when you don't need one? If you got a zone valve job, why put in a three-speed circulator? They're steep curve circulators. The 0015 is a steep curve circulator. The 1558 is a steep curve circulator. The NRF 22 is a steep curve circulator. If you got a zone valve job, why on earth would you put one of those on there? It makes absolutely no sense because you're creating a problem. You're creating a problem when you don't have one. Don't get me started, Mr. McGrath. I know you're going to do that.
Of course,
really,
he yelled it too. He had to yell it.
Yeah, exactly right. Why create a problem when you don't need to? It makes zero sense. Zero sense. If you know it's going to cause a problem, why put it in the first place? So you could just stay flat, man. You could just stay flat. You could just put in a flat curve pump and be done with it. Or you could complicate things needlessly by putting in a pressure differential bypass valve. Every time I talk about pressure differential bypass valves, I start to get a little crazy because a pressure differential bypass valve is not a cure, it is a Band-Aid. Okay, it is the price you pay for a self-inflicted wound. All a pressure differential bypass valve does, and I don't want to get into it because I'll go crazy, is that it turns a steep curve pump into a flat curve pump. That's all it does. That's really all it does. It turns a steep curve pump into a flat curve pump. And if all it does is turn a steep curve pump into a flat curve pump, why not put a flat curve pump in the first place. Okay? This is one of those, I don't know. That's just the way it is. That's just the way it is. Yeah, next week's trivia, how many shades of red can Barbara's head turn? Yes, indeed. Yes, indeed. The other option, of course, is we can adjust and adapt, and that is your variable speed lowdown. This is where variable speed circulators start to come into play. They can do an awful lot of good here. The number one use is not to make zone valves quiet. That's a nice use. That's a great application, but we can quiet down zone valves without going with ECM variable speed. Simply put in a flat curve pump and we got her licked, right? So we don't have to do that. There's a lot of other benefits though that trump that. Okay. So let's take a look at what we have here. Okay. Oop, here we go. It's still with variable speed circulators, people think, you throw them in and it figures it out. Yeah, just put in a variable speed pump. It'll be fine. It'll be fine. That goes to this nonsense that's been propagated out there in the industry that they're somehow magic or that they somehow free you of having to know anything about sizing circulators or system curves or pump curves or anything like that. Because I put in a, I say, oh yeah, put in that. It does the thinking for you. It takes the thinking out of it. It's like magic. Yuck, 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 yuck. And you just want to go, no. That's not how they work. That's not how they work. Regardless of whether it's delta T or delta P. You got to know what this thing that you're holding in your hands does so you can get the most out of it. Let's take a look at maybe the one circulator out there that we can say with a high degree of accuracy that is self-sizing. The Taco VT2218, it is a delta T pump, and it is as close as we have in the industry to a truly self-sizing circulator because it varies its speed to maintain the design for delta T in the system to the best of its ability within that green operating range, right? Within that green operating range. So if you've designed your system to 20 degrees, which in our example, let's say we did 7 gallons a minute, 5 foot ahead for our zone valve system. Now, under design conditions, you're going to, well, in any condition, when you install it, you're going to have a sensor on the supply. That's the hottest water going out to the system. And then on the common return, okay, of the water temperature going back to the boiler. And what this thing's going to do is it's going to monitor the temperature difference between what's going out and what's coming back. And it's going to vary its speed to keep it at 20 degrees. So under design conditions, that coldest day of the year, all my zones calling, all right? Here's what I'm going to have here's what I'm going to have for a pump curve. It's going to be right along here. This is where it's going to be operating, and I'm going to be getting 7 gallons a minute at 5 foot ahead, and I'm going to have a 20 degree delta T. The circulator's never going to work up here. Doesn't have to. On the quote unquote coldest day of the year, this is where it's going to work. Now, and if we were put in our system curve, that's where it's going to intersect. Now, we've got other system curves for other, combinations of zones calling, but we're not going to work up here, up here, up here, or up here. What's going to happen is as a zone closes, my flow goes down. To maintain the 20 degree delta T, the pump is going to slow down and the pump curve is actually going to shift downward. It's going to shift downward as zones close. All right. Pump's going to go slower. The system curve is actually going to change with the needs of the system because remember, GPM equals BTUH divided by delta T times 500. If we know the BTU load is going to change. If the flow rate stays fixed, the delta T has to change in lockstep with the BTU load. But if we fix the delta T like we do here, the BTU load changes. The flow has to change in lockstep with the BTU. It's just simple common sense. So as zones close, we're going to go slower, 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 until we get like our smallest zone. Let's say it's 1 gallon a minute at 5 feet ahead. Here's my performance curve with just one zone calling. And as zones close, I'm going to go down to here. As zones open, we're going to go back up here. Now, as it gets warmer out, this is the other cool thing about delta T pumping. As it gets warmer out, the BTU load goes down, right? As it gets warmer out, the BTU load goes down. Therefore, my required flow rate should go down along with it. We talked about that earlier. Well, This circulator will not only vary its speed with zones open and closed, it'll vary its speed with the weather. Doesn't have an outdoor sensor or anything like that. It just infers the load based on the delta T. How many BTUs am I taking out of the water to replace the heat that is lost in the living space? All right. I need less of it. When it's warmer out, pump's going to slow down. This doesn't fight with outdoor reset. This thing doesn't care what the supply water temperature is. The boiler will set that. The only thing this thing cares about is the temperature difference between what's going out and what's coming back. And it's the best way. The Department of Energy has said this is the best way electronically and efficiency wise to run a variable speed circulator. And from and just from an overall efficiency standpoint, an overall anti-short cycling standpoint, it's by far the best way to run a boiler system. So that's
it's kind of like indoor reset when we stop and think about it for a second.
Yeah.
We could say kind of like, because it doesn't know the temperature upstairs, but it knows how many BTUs have left the pipe. That's the cool thing about it. It knows how much left. So how much left is a function of how much heat left the house, period. Right? And as it gets colder outside, temperature it's all dependent on difference. If it's colder outside, heat transfer happens at a higher rate compared to when it's warmer outside. So as your BTUs leave the house, this circulator says, oh, well, we're going to have to put some more in there. So let's speed up too. And
cool.
And Doug said the other thing too about this circulator, when you have something like this in there, the comfort level changes. Totally changes in a house when you have a circulator that's going to kind of monitor the heat loss of the space, because now you have a very consistent temperature. Normally we see spikes in temperature going up and down, up and down. You have a differential. Thermostat's operating on that differential. What you want to do is try to get a thermostat that has a very low differential, so this way it keeps that temperature nice and comfortable in there. If you were able to dial everything in perfectly, all right, as well as having perfect alignment to the planets and all that other jazz, you wouldn't need a thermostat in the house with a variable speed circulator and a variable speed boiler in there. All right, but your thermostat's supposed to act as a high limit in the house, and it just changes everything altogether. Yeah.
Cool. I like that. It knows, it monitors the BTUs leaving the pipe. I love that. That's a great way of putting it. All right. Way to go, Barney. All right, Bon. Now, constant pressure delta P, there's a lot you see in a constant pressure delta P pump. There's a boatload of individually programmed, algorithmically accurate pump curves built into the system. Okay, there's a whole bunch of them built into that control. But we still have pump curves and system curves, because what we have with a constant pressure delta P circulator is what we call a control curve. In this case, it's kind of the ultimate fixed, it's the ultimate flat curve pump, okay? Let's say we use the Taco 007E. The Taco 007E is a variable speed circulator, but there's no adjustments to it. It's a 10 foot of head constant pressure variable speed delta P pump. So this right here is its control curve. This is where it works. It works at 10 foot ahead constant pressure. So I need 7 gallons a minute at 5 feet ahead. This is what I need, right? This is what I need, but because I'm using a Taco 007E, that's not what I'm getting. I'm getting this. Okay, I'm getting about, well, again, 9.5 gallons a minute at 10 foot ahead. Now, it's actually going to be working on this particular performance curve, or this particular pump curve right here, okay? Now, out here, that's max speed. The thick green line is max speed, and that is 44 watts, so to speak. That's a watt. That's a W, okay? 44 watts. The lowest speed down here is 5 watts. So as we go up in speed, we go up in wattage, but still the max is only 44 watts. Now here, we're not that far off a max. I'm going to bet that's at what, maybe 35 watts. So on the coldest day of the year, I'm heating this structure at 35 watts. I haven't helped myself much delta T wise, but I'm using 35 watts instead of 85 or 90, okay, like I would at the 3-speed pumps at the high speed, okay? Now, as a zone closes, as a zone closes, for like a nanosecond and a half, it's going to act like a fixed speed pump. I'm going to have a new system curve, and I'm going to intersect this pump curve up here someplace, okay? What's going to happen is the system's going to work up here where the new system curve intersects the existing pump curve, again, for like a nanosecond and a half. The circulator itself is going to sense that, hey, I'm pumping against a little bit more resistance than I want to. That's a sign that something has changed. That's a sign that a zone is closed. That's a signal to tell me to slow down. So what's going to happen is new system curve, right? I'm operating up here. This ball is in reality going to go up here and then down here, but it's going to happen so quickly that it's simply going to look like that, okay? And again, the next zone closes. In reality, we're going to go up here and then drop down, but it's going to happen so quickly that it's going to look like that, and so on, okay? Now, with only one zone calling, I'm working on this performance curve, or this pump curve. With all zones calling, I'm up here. So that could be 30, well, let's see, can I do a 3? 35 watts up here. And this one down here might be closer to 20, let's say. All right. Now, by extension, if I chose the Takeo 0015 E3, it's a 3-setting delta P circulator. So I've got low and medium settings as well as high. Now, high is full speed, fixed speed, contractor, no callback mode. But low gives me a flat curve variable speed circulator set at 5 foot ahead, constant pressure. Medium is like the 0070, it's 10 foot ahead, constant pressure. Now this is where knowing what you are holding in your hands, understanding how this thing works, and understanding the dynamics allows you to fine tune that system about as well as it can be done. 7 gallons a minute, 5 foot ahead, bada bing, I'm right there. I'm getting 7 at 5. So under design conditions, I got a 20-degree delta T. Oh, happy day, right? But again, as zones close, I'm going to be intersecting at different points, but still at 5 foot ahead. I'm going to be using at each intersection considerably less electricity. So now I might be maybe maxing out at 25 watts, and at minimum, I could be down around 10 or maybe 12 watts. So I'm really minimizing my electrical consumption, which is nice. I'm keeping, my delta T's are a little more under control. They're not perfect, but they're better than they would have been with this thing set at medium, or with any fixed speed circulator set to whatever setting that you had, okay? We have the opportunity to be much, much better with our delta T.
And that's just the inherent difference between, say, the 0070 and the 15E3. Right. Obviously, with the 7E, you've got one selection.
And it's an easy one.
Right, yeah. And when you get the 15E3, then obviously let's make sure that we've got those 3 choices, make sure we get it to the right mode for the system design, and that's where that's where we're going to really take advantage of putting in an ECM variable speed circulator, right? That couple of minutes to do the math. I mean, we've spent an hour explaining it. Obviously, when you do it on your own, and I say practice on your own home, you'll see how fast it gets. And when John was showing you how to do the system curves before too, and whipped out the B and G system sizer, right? If those of you that are curious, they got an app for that too.
They got an app for that.
Look at that. That's easy. Look at that. You type in the known flow, known head, and unknown flow. So let me do it real fast for you. Right? Let's go. Known flow 3, known head 6, unknown flow 6. Enter. There we go.
24.
Done. Look at that. So if you can't get your hands on a wheel, or if you don't have a wheel, they got a free app to download too. So
there you go.
Just do that stuff fast. And this way you'll just change the whole dynamics of a system if you do the math and make sure the circulator is running the right speed.
There you go. Jim Tamblin asks, are zone valves 2-position or modulating? Your typical hydronic zone valves are 2-position valve, on or off. Some of them might be fast acting, some of them might be slow acting, but they don't modulate, okay? There are modulating valves, But in terms of an electronic zone valve, 99.9% of them are either open or closed. That's really the best. That's how they work. That's how they work. You have thermostatic radiator valves, which aren't technically electronic zone valves. Those are modulating control valves for a specific radiator, which is kind of how they do things over on the other side of the pond. Are they installed over here? Some, not a ton, not a ton. We actually used to have a company that made and sold those, and nobody bought them, so we don't have that company anymore. Okay, let's continue. I think that might be it, and then we get to our yeah, there we go. Our trivia question, our trivia answer. What's tonight's trivia question? What is the name of the lodge that Fred and Barney belong to? Now, let's see how technical we want to get here. All right, because the name of the lodge is the Loyal Order of Water Buffaloes. The Loyal Order of Water Buffaloes. How about that? The Loyal Order of Water Buffaloes. I think a lot of you kind of got close. We got water buffaloes and things like that. Water buffaloes. Okay. James Zampano got it all the way right. The Loyal Order of Water Buffaloes. So did Mark Rosenberg. Dave, you're filling out the wheel. You're going to have to figure out how many, do we just include water buffaloes, or do we go Loyal Order of Water Buffaloes?
I was feeling generous, so I included both.
You are the man. You are the man.
I did.
Right.
Yep. It was close enough. It was close enough.
And the other one, where was Eric? Where was Eric? Eric was at the Cavern Club in Liverpool, England. And why do we care about the Cavern Club, Dave?
Cavern Club. That is I guess more or less the birthplace of the Beatles.
Pretty much, yeah. That's where they were renowned for playing at the Cavern Club. That's where they were discovered by Brian Epstein. So the Cavern Club in London. That's where Eric was tonight. So everybody got that one correct. You're going to have to put that onto our reel as well. So let's take a look. There's a couple of questions. There's a couple of questions in here that we'll talk about as Dave gets the wheels ready. Let me know when you are ready, Dave. Let's see. Boom, 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 boom. If you had a 60,000 BTU zone and contractor A bid the job using 1 inch copper, and contractor B bid the job using 3/4 inch copper, would contractor B have to add feet of head to his numbers because he used a smaller diameter tube? Yes, because he's going to be having to run 6 gallons a minute through, if it's a 20-degree delta T, he's going to have to run 6 gallons a minute through a 3/4 inch pipe instead of a 1 inch pipe. So yeah, there's going to be considerable pressure. There's going to be a much higher pressure loss.
Much higher head loss, and he'd probably have to upsize his circulator, and then there'd be all kinds of, could be all kinds of challenges after that. So,
right, at 6 gallons a minute, 6 gallons a minute through 3/4 inch copper may be pushing the limits of velocity noise concerns and possible erosion concerns. So if that's kind of where you're going with that, Jay, that's how I would personally look at it. 60, 45, typically you're looking at about 4 to 4.5, maybe 5 gallons a minute through 3/4 inch copper at most. All right. That's about as much as you want to try to shove through there and stay within velocity guidelines. You go to 6 gallons a minute, you're going to make some noise, man. It's going to be a noisy zone, and you're going to potentially erode that copper from the inside out, particularly at fittings and changes the direction. And you're going to have a sprinkler system, basically. And that's a no good. That's a no good. All right.
So Doug added on to that. He's like, what about getting heat to the end of that zone? Well, that's what the constraint, keeping it to a 20-degree delta, right? So,